core, an image is simply a visual representation of an object, a concept, or a scene from the physical world. When we look at these scenes, our human eyes process them intuitively. We experience a continuous, seamless flow of light, where shadows blend perfectly and colors naturally merge into one another. But physical art is trapped in its medium. Once the pigment hits the paper, you cannot instantly beam that canvas across the planet, and you certainly can't tell the paint to dynamically change its lighting after it dries. Computers, however, are completely blind to physical paint and continuous light waves. They operate strictly on binary logic and mathematics. So to bring the rich, analog world into a digital environment, we have to find a way to forcefully translate that continuous reality into a rigid, highly structured language of numbers. We do this translation every time we take a photo. In a fraction of a second, a digital camera freezes a massive, continuous scene. This diagram outlines the core difference between the two formats. Looking at the analog side on the left, you can see how an image like a chest X-ray represents the continuous nature of human viewing. The brightness and film density exist on an unbroken spectrum. To translate this for a computer system, the camera performs a process called sampling. It throws a massive invisible grid over the entire scene, dividing that continuous analog light into thousands of tiny, separate boxes. The exact shape and dimensions of this specific grid, how many boxes wide versus how many boxes tall, is known as the aspect ratio. But merely throwing a grid over reality doesn't actually capture the picture. It only builds the empty containers where the data will soon live. Which raises the question, what actually happens inside one microscopic box of that newly created grid? This is where quantization comes in. Quantization is the precise process of measuring the analog light inside that single box and assigning it a definitive numerical value, like the integer 57. Every nearby box undergoes the exact same measurement. Because shadows and highlights subtly shift across a surface, the adjacent squares receive slightly different numbers to reflect those variations in brightness. The total vocabulary of numbers the computer is allowed to use for these assignments is determined by its bit depth. A system with a low bit depth has very few numbers to choose from, while a higher bit depth gives the computer a massive pool of integers, allowing it to record much smoother gradients. From the computer's perspective, it does not see a photograph of a dog or a suspension bridge. It only sees a massive, highly organized spreadsheet of numbers. Why go through all this computational effort? Why slice up a perfectly beautiful reality just to turn it into raw math? Because once an image is purely mathematical, it becomes infinitely malleable using basic arithmetic operations. If you want the picture to be brighter, you don't need a stronger light bulb. You just add 10 to every single cell in the grid, and the visual blocks instantly brighten. You can apply a spatial filter to average out a cluster of numbers. By finding the mathematical middle ground of a specific area, the computer can seamlessly remove a visual blemish or smooth over a harsh, jagged edge. Every time you apply photo filters, explore a 3D video game world, or export a digital design, the software relies entirely on manipulating these exact numbers. The entire field of computer graphics is ultimately a carefully calculated illusion. We use discrete, rigid mathematics to precisely arrange millions of tiny squares of light, perfectly tricking our continuous analog human eyes.